Okay, so hello everybody, and thanks once again to the organizers for giving the opportunity to present one of our recent topics. And the title is Selective Hydrogenation of Aliphatic Amides to Amines over Heterogeneous Catalysts. So during my talk, this is going to be the outline. I will first give a brief interview of our organization, Solvay, and Solvay One Planet goals, and also go on to give a brief overview of E2P2L, which is Eco-Efficient Products and Processes Laboratory. And I will go further into the details with one of a case study, which I will highlight today, which is hydrogenation of aliphatic amides. I will show catalyst screening and some examples of catalyst characterization and the influence of different reaction variables in this reaction, as well as substrate scope. And finally, I will wrap up my talk with the conclusion. So just to give you a brief introduction, for some who already know, Solvay, it is a science company whose technologies bring benefits to many aspects of daily life. And our innovative solutions, they contribute to a very wide spectrum of application fields, which are highlighted here. I will not go much into the details. And our group, it seeks to create sustainable shared values for all, notably through what we call the Solvay One Planet goals, which are crafted around the 3 pillars. I will give an overview on the next slide. And these are just some of key figures for our company. And what is the Solvay One Planet goals? These are basically 10 ambitious objectives set up by the leadership of our organization to reduce our global impact. They are basically categorized into 3 main pillars, which is the climate and the resources, as well as improving a better life. I will not go too much into the details, but what I just want to highlight is one of the 4 objectives which have a direct relationship or direct related to catalysis, chemical engineering, and technology to improve some of these ambitious objectives. And introduction about our team, E2P2L at a glance. Just to go through diagonally, our team is international with complementary skills, and we are one of, we call ourselves the Catalysis Laboratory of Solvay, and we are basically a consortium with different scientific partners, mainly academic institutes all over the world. So now going to the topic, or the case study on hydrogenation of amides. It is basically the hydrogenation of amide functional group using molecular hydrogen in the presence of a catalyst, and you can fine tune, the reaction variables or conditions, mainly temperature or the pressure of hydrogen, as well as the solvent to obtain your targeted product. And the good thing about this reaction is that it is an atom efficient and environmentally burning process, as water is the only byproduct generated in this reaction. However, we know that for the hydrogenation of carboxamides, it usually increases the difficulty as you go from a simple, let's say, amide or carboxamide functional groups to the amide on the far end, which is the most difficult carboxamide functional group to be hydrogenated, mainly due to the stabilization effect of the pi electrons in the carbonyl group. by the conjugation with the nitrogen atom. This is why we believe that if we can be able to target and successfully hydrogenate the most difficult functional group, then it should, in principle, be relatively easier to do the hydrogenation of other functional groups within the spectrum. In the prior art, there are some few examples which have been reported which can successfully hydrogenate the amide functional groups. However, harsh reaction conditions are required for this reaction. Typically, temperatures more than 250 degrees Celsius and 300 bar of hydrogen pressure on copper or chromium-based catalysts. And the target for our reaction is to be able to achieve the selective hydrogenation of this functional group at rather moderate conditions, which are industrially relevant. And we believe that an optimum hydrogenation catalyst for amide could be very efficient for reduction of other functional groups, which I have just mentioned here, carboxylic acid or esters or anhydrides, which may also be derived from renewable sources. So the first part, we conducted the catalyst screening for the hydrogenation of N,N-dimethyl-dodecanamide. It's an aliphatic amide, functional groups of different monometallic as well as bimetallic catalysts. So we noticed that with monometallic catalysts, which are usually applied for activation of hydrogen in hydrogenation reactions like palladium or platinum or rhodium catalyst, usually for the carboxamide is very stable. We have little or no reaction at these conditions using these catalysts. And by modifying the monometallic catalyst to bimetallic with oxophilic centers such as molybdenum or vanadium to obtain, in this case, palladium molybdenum or palladium vanadium, we have some slight improvement in terms of activity and yield. However, not very significant. We obtain about 30% conversion and 25% yield of the target product. And with the platinum, with molybdenum, very little increase in activity. With the vanadium, yes, a significant increase to about 40% yield to the target product. However, with the rhodium catalyst, we noticed that there is a significant or a dramatic rather increase in the catalytic activity using the modified rhodium catalyst with molybdenum or vanadium. And in this particular case, we are more interested in vanadium since we obtained the best catalytic results using the modified catalyst up to as much as 95% at rather moderate conditions of 130 degrees and 30 bar of hydrogen within 1 hour in DME as a solvent. So we were more interested in these, and I will show some detailed catalyst characterization on this bimetallic modified catalyst. So in this slide, it shows some different physicochemical properties of the rhodium vanadium catalyst. And we further on conducted a systematic study to show the direct, I would say, impact of the rhodium and vanadium in the bimetallic catalyst, starting with only the support material, alumina, which has no activity at all. And the rhodium, we see some slight activity at 4 weight% of rhodium on the supported metal catalyst. And as we put the second additional metal, we also varied the molar ratio from 1 to 0.5 to 1:2 of vanadium. And we see that we obtain an optimum, I would say, catalytic activity at 1:1 molar ratio between the two metals. And the dispersion was also optimum in between I would say the starting dispersion in rhodium and the maximum dispersion, or rather the minimum dispersion, which is obtained when you put too much of vanadium into the bimetallic catalyst. And we also noticed that when you conduct the hydrogenation reaction using only vanadium, it's not sufficient. Although vanadium, we believe it is an oxophilic center. However, if you do not have the hydrogenation active site, you will not have any catalytic activity at all in the hydrogenation reaction. So the two active centers are necessary, or you actually need to have a synergetic effect or interaction between the hydrogenation rhodium side as well as the oxophilic vanadium side, which delocalizes the charge in the carboxamide functional group, making it easier to hydrogenate the carboxamide functional group. And we have conducted the characterization on the bimetallic rhodium vanadium catalyst. Here, just to show you some examples on hydrogen temperature programmed reduction profile, which shows that it is very easy to reduce the rhodium catalyst into metallic rhodium, which is necessary for the activation of hydrogen, even at the reaction conditions. So you can indeed do the reduction of the catalyst in situ at the reaction conditions. Approximately 130 degrees is sufficient to reduce the rhodium into metallic sites. And further on, we conducted also CO FTIR analysis. And when we compare the two spectra of the monometallic and bimetallic catalyst, we show that when you have rhodium vanadium catalyst, it exhibits low intensity, particularly on the bridge bonded CO, which comes at about 1,818 wave number, illustrating that the interaction of the metallic rhodium and oxophilic sites, it suppresses these specific sites for the bridge bonded CO. And the TEM micrographs of the bimetallic catalyst, they were also characterized by high metal dispersion with the average particle size around 3 nanometers in the bimetallic catalyst. And on the next slide, just to show some influence of reaction variables, we show that in the hydrogenation of the amide, the selectivity towards the desired amine, it remains very high, independent of the conversion. So we don't form side products, mainly due to carbon-nitrogen cleavage. And the influence of hydrogen pressure, it also shows that it does not have any impact on the selectivity towards the desired product. It rather affects only the extent of the amide conversion and not selectivity towards the desired product. And on the next part about the catalyst stability, the catalyst, it was used for 7 cycles. And within the first 4 cycles, there was no apparent loss of catalytic activity. And at these conditions, the catalyst was just recycled without any pre-treatment. However, after the 4th cycle, we start to see a progressive decrease in the activity. And after the 7th cycle, the overall yield reduced to 74% after the 7th cycle. And when we did the analysis of the catalyst after the 7th cycle, before any pre-treatment, for example, by TGA, we noticed that there was some weight loss due to thermal decomposition. We believe it's carbonaceous deposits in the catalyst, typically detected at around 260 degrees Celsius. And we believe that if we indeed need to reactivate the catalyst, it should in principle be feasible just by removing the coke which is generated on the catalyst. And last but not least, we conducted a representative substrate scope just to show the feasibility or the activity of the catalyst on different types of amides. When we change the length of the aliphatic amide to a shorter chain, there was no significant difference in the activity. So as long as the amide remains a tertiary, the overall yield or the maximum yield which can be obtained remains rather high, more than 95% in this case. However, we noticed that with secondary amides, yes, there was a slight decrease in the maximum yield up to 95%. And when we changed from secondary to primary amides, there were much more challenging substrates to be selectively hydrogenated. And we believe that it's mainly due to the less activated nature of the carbon-oxygen and carbon-nitrogen bond in the primary amide. And in the case of aromatic amide, we also noticed that it's rather easy to do the complete hydrogenation of the aromatic ring together with the amide functional group. So to finish up my talk, I will share with you the conclusion that the selective hydrogenation of tertiary and secondary amide, it was investigated, and by modifying an industrial catalyst with impregnation of vanadium species, was demonstrated to obtain an efficient bimetallic rhodium vanadium catalyst. And the catalyst, it was well characterized using several techniques, which I shared to elucidate the nature of the active site. And we believe that the strong synergetic interaction of hydrogenation rhodium metallic site and the oxophilic vanadium site in the bimetallic catalyst is the one which is beneficial for the selective dissociation of the carboxamide functional group. And the bimetallic catalyst, it can achieve more than 95% yield of tertiary and secondary amide at rather moderate reaction conditions compared to the prior art of copper chromium based catalysts. And last but not least, I would like to thank my colleagues which participated in these projects. Alex, who was a master student, and Yazid and Stefan, who worked together at the EGPTO team, and the rest of our team in front of the building of our laboratory. And I thank all of you for your kind attention.
Yes, thank you, Dr. Bright. Is there any questions from audience?
Yes, good morning. This is Joe Marola. I am just curious as to what you think about the very large price hike of rhodium and the rhodium shortage means for further development of this catalytic system.
Yes, that's a very good question. Yes, indeed, we know, of course, that the price of the metal, in this case, rhodium, it may have a significant impact in the overall cost of the, I would say, the process using the rhodium vanadium catalyst. However, usually for these kind of projects, for further development, we usually conduct our own, I would say, cost assessment for the process to evaluate, even if the price of the catalyst might be high, but would it be competitive as a process when we compare it to a much cheaper copper chromium, however, at a much harsher production costs. So it is a very important parameter to be considered. And we of course, yes,